Let's go lab. And just make sure the audio works here. Get an infinite amount of reverb. I believe that should be good. Okay, I'm going to pop out the chat. Let's get this out in the chat. So for those watching this in the future, we are doing this on Twitch. And what we are going to do is do some PyTorch experiment tracking. Do some solutions, that is. So I'll just get everything set up here. But this is all going to be live. That way you can sort of see what it's like to troubleshoot different things and whatnot. Might just minimize that. Oh, just make sure I'll have that up so that if I go offline, I'll be able to tell. Okay, beautiful. So here we are at the PyTorch Deep Learning repo, which is going to be a PyTorch course coming up. But we've done several of these kind of streams in the past, namely going through the exercises for each of these. And so what I've been working on is PyTorch Experiment Tracking. So this is an important concept in machine learning in general because machine learning is very experimental. So you need a way to be able to track your experiments. And so all of the information for this is at learnpytorch.io, at 07 PyTorch Experiment Tracking, which is over here. It's currently got work in progress there because we need to finish off the exercises and solutions. So namely, you'll be watching or you'll be going through this video or going through these solutions after you've already gone through all of this material. So this is covering several different modeling experiments using PyTorch and tracking them with TensorBoard. And the main experiment that we're tracking is our model's performance on a project called FoodVision Mini, which is an image classification model to classify different images of food. So if you go through all of this, here's the experiments that we run in this notebook. We run 8 different experiments. And this is really cool because it's using the latest version of the PyTorch TorchVision API, version 1.0.13, which has a new multi-weight API. What that means is you can use multiple different pre-trained weights with the same model code. I'll go through that in a second. Essentially what we're doing here is we're going right down to the bottom of this section. We've been through all of this material. And now we would like to go through the exercises. So come right down here, main takeaways, exercises, beautiful. So this is the last little thing that I have to do for this, that we're going to do together. We have an exercise template notebook for number 7. We have an exercise example solutions notebook for 7. This is section 7. And there'll be a live walkthrough on YouTube later on, which is the video that we're recording now. We're doing this live so you can see how I troubleshoot different things. So here we go, PyTorch Experiment Tracking Exercise Solutions. Welcome to 07 PyTorch Experiment Tracking Exercise Solutions Notebook. All of the exercises in here are based on the material in section 7. So that's just letting us know there. And number 1, exercise number 1, all I've done is just taken this, the exercise from here, and put it into this notebook. So pick a larger model from torchvision.models to add to the list of experiments, for example, FNet B3 or higher. There is another thing that we kind of have to do here to get set up. So let's just start writing some code and get set up here. If you're joining in, let me know if you can see the screen, but I believe you should be able to see it. I am sipping some tea because it helps you write better code. So we need to import Torch and TorchVision. So some things to be aware of is the main thing that we need for this. I believe Google Colab doesn't yet have PyTorch's, TorchVision version 0.13 is not out yet officially. So we need to install the nightly version of PyTorch. We're doing that because TorchVision's about to get quite a big upgrade in terms of using pre-trained models, so I'd rather us go through that than use the old version of the API. So let's just set this up. Yeah, there we go. We got 1.11 for PyTorch, and we got 0.12 for TorchVision. However, if we go to the TorchVision documentation, we can see that version v.12 stable release, which is what we've got here, we actually want main, which is the unstable release. So if you compare these two, I'm not going to go through all the differences. The main difference here between the latest version of TorchVision is the models and pre-trained weights. So yeah, here we go. This is what we want. As of v.13, version 0.13, TorchVision offers a new multi-weight support API. So this is a blog post announcing it back at the end of last year, which is December 22, 2021. So the old way of instantiating a pre-trained model is you would just set pre-trained equals true. Yeah, there we go. Pre-trained equals true. Now you can pass in weights as an enum and set up your models with certain different weights. So that is helpful as it allows the PyTorch team to upload different versions of model weights, pre-trained weights for different models to the TorchVision package so that you can choose what pre-trained weights you'd like to use. So say there was an update on the best performing weights for ResNet 50, they could be updated to the latest weights. So weights.default is, I believe if we go in here, if we go to .default, yeah, .default is currently the best available weights. So if we just choose .default, we're going to get these weights here, ImageNet 1K V2, which is the best performing weight. So that's, if you want the best performing, you just have to keep default in mind. So from version, I believe it's 0.15 onwards, the old way of doing things is going to be obsolete. So that's why we are going to install the nightly versions of PyTorch so that we get this updated API. How do we do that? Let's go to PyTorch getting started. If you want to install the nightly versions, now keep in mind you don't have to do this step if you have TorchVision 0.13 plus. You don't have to do that if you have this. So you can install PyTorch nightly versions by going preview nightly Linux if you're in a Linux environment, and you can use Conda or pip. We'll probably use pip. And then if we want GPU access, you'll want CUDA 11.3. So we can run something like that. However, I've got the code set up here to do so. So I'm just going to copy this in. What this is going to do is going to be a try and accept block. So I'm just going to write down here. This notebook requires Torch V. We might as well get the latest version of Torch as well. So we don't have those right now. So what this is going to do is it's going to try to import Torch and TorchVision. Then it's going to make an assertion that the PyTorch versions are above a certain number. And if that assertion doesn't fulfill, it's going to go to this extent. So let's just run this. It might take a minute or two in Google Colab. Let's just see what happens when we run this. So there we go. We get some info. TorchVision, Torch/TorchVision versions, not as required, installing nightly versions. So if you have the correct versions of Torch and TorchVision for this notebook, this code should run without installing anything. You can update this to see if you need to, but because TorchVision v 0.13 is not out yet, we have to install the nightly versions of PyTorch. So I'm just going to let this run for a bit. And then we might as well start getting ready. I'll leave this run over here. We're going to import. So this is just going to section 7, PyTorch Experiment Tracking. We're going to get all of the regular imports. We're also going to make sure that we get our going modular scripts. So these are some scripts that we wrote in section 05, PyTorch Going Modular. And they're all available on GitHub under PyTorch Deep Learning Going Modular. So the whole idea of the Going Modular section is to take your most useful notebook cell code and put it into a Python script so it becomes usable or reusable, sorry. And do not tell me my internet is dropped out. Goodness gracious me. My internet's been on the fritz lately. Okay, we should be back online. So yeah, here we go. This is our going modular scripts. We have data setup.py, engine.py, model builder, predictions.py, train.py, and utils.py. So that's what we want to import with this line of code here, or several lines of code. Basically it says if these things don't exist, download them and import them. So yeah, as you can see, this is downloading the latest versions of Torch Vision, Torch Audio. We don't actually need Torch Audio, so we could have got rid of that one, but that's okay. And here we go. Installing packages. So it's uninstalling Torch 1.11, and we're going to get the latest version of PyTorch, which is the nightly version of 1.12. And after this is finishing installing, we may have to restart our runtime. So we'll just get that set up. And create a helper function to set seeds. We'll probably get the data as well. So what do we have to do? What's our first exercise? Pick a larger model from Torch Vision models to add to the list of experiments. For example, FNet B3 or higher. So yeah, we have to pre-process all the data first. So we basically have to run all of the code here to get up to this exercise. Because if we go down to this section, remember these exercises are based off this notebook here. This has got some information. What kind of experiments should you run? I mean, there's machine learning. You could run as many experiments as you could build models. There's no limit to the number of experiments you could run, but of course you can't try everything. So the best way to do it is to keep your experiments small and scale up when necessary. Here we go. So we installed some new packages, the nightly versions, but now we must restart the runtime to have them available. So this is going to restart the runtime up here. And I'm just going to make sure I have a GPU. Yes, I do. And so if we run this, we should now have the latest versions of PyTorch. There we go. Torch version 1.13. See how it's a developer version, so it's the nightly version. And we have Torch version 0.14. Now this block of code will work by default. You won't have to install anything once these versions come out. So just keep that in mind going forward. And I just want to make sure we have a GPU. So device equals CUDA. Device, we'll get our regular imports. So couldn't find Torch info, that's going to give us a good printout of our models. Couldn't find PyTorch going modular scripts, so downloading them from GitHub. Beautiful, we're cloning all of the repo here. And there we go, beautiful. So if we import PyTorch now, wonderful. So now let's get the data. This is not really, I'm not going to put this in the exercises because we're just copying code here. We'll get a helper function here to set the seeds. Or actually, did we get helper functions.py? Doesn't matter. We'll set the seeds. So this is just a helper function to set the random seeds. So you can just go set seeds for PyTorch manual seed and CUDA manual seed. Nice and simple. And we'll get the data. So now we've got the data. Beautiful. And so if we come down here, we ran a list of experiments. So we need to get a pre-trained model. Getting a pre-trained model. Here we go. Setting up a list of experiments. Here's the experiments we ran in the notebook. So we did 8 different experiments with different levels of data. So 10% of the data of pizza, steak, and sushi images, or different levels of model or different size of model, EfficientNet B0 or B2, and different numbers of epochs. So 5 epochs or 10 epochs. And so the first experiment used the least amount of data, the smallest model, and the least number of epochs. But we slowly worked it up to, by the end of experiment 8, we were running with double the amount of data, double the amount of parameters in our model, and double the amount of training time in PyTorch Experiment Tracking, that is. And so now, this first exercise is to set up a larger model from torchvision.models to add to the list of experiments. So let's have a look at TorchVision models. So here we are. Now, just remember, if this is not on version v.13 or higher by the time you watch this video, you make sure you have to go to the version of the documentation that is the latest, so that it has PyTorch's multi-weight API here. So we're going to go into model and pre-trained weights. So there we've got different models, ResNet 50 and ResNet 50 weights. That's a major update for the latest version of TorchVision. Yeah, so this old way of doing things is deprecated. So the new way of doing things is passing in an enum of what weights you'd like to use. So here's all the different models we can use for classification. So RegNet, ResNet, ResNext. We've been using EfficientNet. Hell, we could even use EfficientNet V2 if we wanted to, or a Vision Transformer, or a Swin Transformer. But then if we go down here, we've got all the results. Look at all these different models that are in there now. So we've been using for our experiments EfficientNet B0 and EfficientNet B2. So generally Oh, Christopher, saying the video is lagging, but the voice is good. How is it now? Can you still hear me? So generally, the higher the model number, the bigger the model. Or if you've got, like, say, an adjective, say large, small, tiny, we want one that performs better than EfficientNet B2. So this is the current one we're using, the bigger version. So how about we bring in conv next? How many parameters do we have? So that's 9.1 million. We want a bigger model, so maybe, but not too big, you know? Well, EfficientNet B6 is less parameters than conv next small. EfficientNet models are actually really good for their size to parameter ratio. Maybe we could bring in EfficientNet V2M. How about we try that one? Or even EfficientNet V2S. So 9.1 million. Let's double the number of parameters. Let's try EfficientNet V2S. Let's try this one. So these are all different models you could try, right? You don't have to necessarily use EfficientNet. I've just found that in my experience, EfficientNet models are quite... And now there's a V2 version of EfficientNet, by the way. So EfficientNet V2. So small, medium, large. You have to keep the size of your model in mind, because depending on where you want to deploy it, if your model's too big, you won't be able to deploy it to, say, a mobile device or something like that. So you could troll through these models and find the best power to weight ratio, as in, like, whatever its best results versus how many parameters does it have. Ideally, you want the best performance with lowest number of parameters. So wherever that point on the curve is, that's your ideal model. So let's just pick one. I'm going to pick EfficientNet V2 small. Where were we? We'll go back to Colab. Go here. Let's try I'll just get this up out of my face. EfficientNet V2S, which stands for EfficientNet version 2 small. I'm going to go here in Notebook 07. Is this text big enough? We tried out FNet B0 and FNet B2 with, I think it was 4 mil parameters and about 9 mil parameters respectively. Let's try step things up by using a bigger model. Which has 20 million parameters. So parameters, recall, are weights of a model. So parameters, the more weights, the more parameters a model has. In theory, the more opportunity the model has to learn representative patterns in whatever data you're working with. So let's try this. So we'll go FNet V2S equals, now what is the code here for this? I'm just going to import TorchVision here. Models. We want models.EfficientNet V2S, and then we can get, we need to get the weights first. So this is the new API here, right? Is my face in the way? So the new API, we get the weights by this. You can go ImageNet 1K V1. So here's the accuracy that those weights get, 84.228 on ImageNet, which is 1,000 different classes. And generally it takes a size of image as 384. Okay. Well, that's all right. We can just use a generic size of 224 for all of our models. But this is just to let you know that these weights were acquired using this training size here. So let's just create the weights. So we can go models dot, we'll get the enum. I believe this is the enum type, Python enum. EfficientNet V2. And S weights. Now, if we call .default here, .default means the best available weights. So rather than calling some other version like ImageNet 1K V1, if you call .default, this is with the new API, by the way, equals best available weights. So small, and then we'll go weights equals FNet V2 S weights. And then we'll have a look at FNet V2. So it's going to download the pre-trained weights. There we go. Beautiful. So we get all these layers here. I'm just going to comment this out. How about we get a summary from Torch Info. Import summary. So we'll get a summary of FNet V2S, and the input size can be by default 13224 224. And let's just have a look at the input and output shapes of our model. So this is really helpful, right? EfficientNet, we get a 1 and 1,000 output shape. So the 1,000 is for the classes in ImageNet. And then if an image of batch size 1, 3 color channels, height and width of 224, 224 goes through it, it's going to get manipulated in several different ways, going through multiple different layers of convolutions. And we see here that we have about 21.5 million parameters versus EfficientNet B2, which has about 9 million parameters. So let's set up our other modeling experiments, because this is what we want to do. We want to add this model, EfficientNet V2S, to the list of experiments we've already done. So by the time we've finished, we're going to have 12 different experiments here. Is that the best way to do things? Maybe we can EfficientNet B0 and we just put EfficientNet B2 versus each other. EfficientNet B2 versus EfficientNet V2S. So EfficientNet B2 is in bananas 2 versus V2. Oh my goodness. There's a lot going on there. But let's just see. We need a function here to... Yeah, we need a way to track our experiments. So we'll bring in the create writer. Yeah, I'll show you here. So create writer has no attribute TensorBoard. Hold on. Torch.utils. Oh, is this because Torch has been updated? Import. So we need to create a summary writer because we want to track our experiments. So that's our Torch summary writer. Tracks experiments. Yeah, why is this not from torch.utils import TensorBoard? No, we'll go dot TensorBoard. Well, we don't, maybe we'll just get rid of that. There we go. Okay, so now we've got a writer. This is going to save our models. I might just import this here. So the whole thing we're trying to do here is track our experiments. I'm going to write on this side of things so that my face stops getting in the way. Import summary writer. Let's try it out. Writer equals. So if we type in experiment name equals test experiment name, and then model name can be this is the model name, and then extra, add a little extra if you want. So this is going to create a writer. Yeah, there we go. So that's going to save the runs to test experiment name. This is the model name, add a little extra if you want. There we go. Beautiful. So now we also need a modified train function to make sure that we can log our experiments. So this is what we did we created this function train in section 5, going modular, And what it does is it does a train step and a test step. And so these functions, if they're defined as well up here, they're defined in going modular.engine, train step and test step. So we might bring this in here. So we can look at those, going modular engine. If we go into going modular engine. So we can see this train step. So train's a PyTorch model for a single epoch. So it just goes through the PyTorch training steps. So it does the forward pass, calculates the loss, optimizes zero grad, loss backwards, optimizes step. And then we've got a test step function. And then we've got a train function, which combines the train step and the test step together, prints out the results. However, we want to add functionality to this train function so that it can use a writer here. So for example, writer, and it can track experiments to that writer. But we're not going to modify it there. We will just modify it in our notebook. So we'll get rid of that. And we'll create a new train function here, which I've already prepared earlier. So add writer parameter to train. I'll just show you what's going on here. So all we're doing is that's the same function. Basically everything up here is the same, except for the fact that we're taking in a writer now as a parameter. And then we are using the writer here. If there's a writer, if it exists, we're adding our model's results to that writer. So we're already tracking the loss and the accuracy. So we're updating the writer with scalars for the loss values, so the train and the test loss. And we're also updating the writer here with the accuracy values with the train and the test accuracy. Then we're closing the writer. If a writer doesn't exist, we pass and we still close the writer. Do we need that again? I don't think I need that extra writer there. I think that's overkill there. I'll get rid of that. Maybe I'll just get rid of that too in the actual notebook. So this is my Lambda Labs. So we want, this is the actual notebook here. Close the writer. We want writer.close. We don't need two of those. I think closing it there is fine. I'll just save that. That way that'll get updated on the book version of the course. So now we have a train function ready to go, and we want to go back to here. We've just copied in that. So now we have a few pieces of the puzzle. We're working towards using a larger model to compare that. Let's compare it to keep things simple. Let's just compare FNet B2, best performing model, to FNet V2S. I'm going to call this FNet V2S for short. So we've got that there. We need a function to create. We'll get the two extra data sets. Download those. Create those. Hey Siobhan, what's going on, man? I've been excellent, thank you, my friend. It has been a while since I've been on streaming on Twitch, but we're doing some exercises here for PyTorch Experiment Tracking. I'm going to create all of these data loaders. So let me just step through the code here one more time so we know what's going on. So import transforms. So the main transform we need to do here is make sure, because we're using a pre-trained model, because we're using transfer learning, we need to make sure our data is formatted with the same distribution as what our models were pre-trained on. Otherwise, we can see performance degradation. So let's create a transform to normalize data distribution to be in line with ImageNet. So the models we're using, EfficientNet V2 and EfficientNet V2S, are pre-trained on ImageNet. So we're going to create a normalizer transform. Normalize. And we'll just use these values here. So this is the values, the mean values and the standard deviation values across the color channels. So one value per color channel. This was calculated using a small portion of the ImageNet dataset. If you'd like to read more about that, that's in the PyTorch documentation. And so that we can compose now our transforms into a pipeline. So create a series of transforms or a pipeline. I have been working busy on the PyTorch course. It's getting very close to the end. I've got 2 notebooks ready to go. Oh, sorry, left to go. But I'm pretty proud of it. If you go back through all of these sections, there's a fair bit going on here. So let's create a pipeline. Simple transform equals transforms.compose. And, oh, thank you, Christopher, for linking that. This is the link Christopher just sent through. Just sent through the link to PyTorch Experiment Tracking at learnpytorch.io. I really like the ability to turn a Jupyter notebook straight into a book or a blog post kind of thing, because that way you get like the best of both worlds. You get to explain what's happening and you get to see the code running. Normalize. So now we've got 3 steps here. We're resizing our images. We're going to use an image size of 224, 224 for all of our modeling experiments. We don't necessarily have to do that. It could be 300 by 300. It could be almost any value we wanted to, but 224, 224 is quite a common one you will see. Of course, the bigger the image size, the longer your models will take to compute. Then we convert our images to a tensor, and then we normalize them. So we convert them to a tensor. This will get image values between 0 and 1 because that's what neural networks like. Beautiful. Now we got one more step to do. We need to create some data loaders. Oh, and then we'll create some feature extractor models. That's fine. We can do that. So let's just create, we'll use the same test data set for both, or test data loaders. After many years of ML, does it get old? We've got a question here. Does it ever get old? Well, actually, I realized the other day I was going to do a post of some sort, but I haven't. I'm trying to be offline until I finish this course. I'm just going to write in some batch size here for 32. Just going to start creating some data loaders. I realized a memory came up in my Photos app and said, it was a video of me training my first neural network in my friend's lounge room 5 years ago. So I've been in machine learning for 5 years. That's crazy. And no, it doesn't get old. It hasn't got old yet for me. Create data loaders, and we need a train directory, which is going to be trainer. Do we have different training directories for? Yeah, we do, 20%. So the difference here, we've set up directory paths for, we're using 2 different data sets here, just like we did in the notebook. So one of them is with 10% of the images from Pizza, Steak, and Sushi from Food 101. The other one is with 20% of the images. So these experiments have double the amount of data as these experiments. So again, what we're testing here, we're trying to evaluate how much more data influences our model, how much more model parameters influences our performance, and how much training time influences our model performance. So let's keep pushing forward. We've got create data loaders. We're going to create this one for 10%. So trained 10%. And again, we're using the same test directory for both models. or for all models. That way we keep our experiments. The transform is going to be the simple transform that we created above. And then the batch size is going to be, of course, batch size, the faithful 32. Lovely. Might just create this a bit bigger. There we go. There's our transform pipeline. Now we go create 20% training and test data loaders. So my biggest fear, this is a quote from the chat, is that something you enjoy becomes something you no longer enjoy. Oh, yes. But that's a circle of life, right? For something new to come into your life, something old has to die. We go class names. Both of these, just to reiterate, both of these use the same test data set. So data loaders, we want trained-er. So the main thing we're testing here is if we increase our model size even more, do we get better results? Because EfficientNet V2S is twice the number of parameters as EfficientNet B2, B for bananas. Tester, so see how we're using the same tester for both of these. Transform equals simple transform, and batch size equals batch size. Wonderful. We can run those. I think there was some helpful printouts in the notebook to tell us how many batch sizes we have. And now, this is the important point. I say this a lot, but these exercises are based on all of the code that we've done here, so feel free to reuse any of the code that we have in the notebook. And I'd encourage you to do so rather than reinventing the wheel from scratch. If there is something that you'd want to practice, you should rewrite the code, but if it's just printouts, you don't have to rewrite all of that again. Okay, so now we have some data sets. We need to create some models. Create models. Or maybe we're finally here. Create models. And I need to go and blow my nose. I'll be back in a minute. So, it's just become winter here in Australia, and I get it like once a year. My nose just gets blocked when it gets colder here. But that's beside the point. Let's keep coding. We need to create some feature extractor models. So in 07 PyTorch Experiment Tracking, we created one for EfficientNet B0, which is actually probably my favorite baseline model. I just have a soft spot for it, you know? And then we have EfficientNet B2. So we want to swap EfficientNet B2 to be model number 1, and we want to put in here as model number 2 is our EfficientNet V2S. So we're doubling the parameters again. And the beautiful thing about EfficientNet V2S is that it has the same number of in features in the classifier head as EfficientNet B0. So there we go. Yeah, there we go. 1280. So that's the classifier head, I believe. Let's have a look at this. FNet V2S. So we can inspect this model. Look how many different components there are in there. Yeah, the classifier head. So let's create two functions, very similar to what we've done in here for instantiating new instances of our models. So here we go. A number of out features for each class. I think we could even functionize this even further. Maybe in a dictionary? Because Because, yeah, we use this in a loop coming up. The only thing is with EfficientNet B2 that the classifier head is a little bit different to the classifier head for. Does this have dropout? Let's have a look. FNet V2S classifier. So we got dropout there. Okay, let's create some functions similar to this. How do we turn this into a dictionary? So if we could pass in there the name of the model. Let's try this out. Let's just functionize this. Def create model. And then we'll go model name equals, it's going to be a string. And then we will go out features equals len class names. And we will go, let's go if model name equals fnet b0 or b2, sorry. Let's just set a few variables here. We could actually do this with the class, but scratch that. So weights equals torchvision dot models dot EfficientNet b2 weights dot default, and then we're going to go model equals torchvision dot models dot EfficientNet. I always get a little bit dyslexic when I'm typing out EfficientNet because there's so many I's and E's and N's. Weights equals weights, and then we need a value here for the dropout. Dropout equals 0.2, and then in features equals 1280. Well, actually, we need EfficientNet B2 here. There, and then we're going 1408. Else we want 02, and then we want 1280. So this is coming from this one. So this is, let's go here. Assert model name equals fnet b2 or model name equals fnet v2s. And then we go here. Should be fnet b2 or fnet v2s. Wonderful. 1280, but I want to change this to EfficientNet v2s, and this will be EfficientNet v2s weights equals weights. Is that correct? v2 v2s, yes, yes, yes. And then we can go freeze the base model layers. So for param, let's just make this bigger. For param in model.parameters or model.features. So we're going to freeze the feature backbone. dot parameters. We want to go param dot requires grad equals false. And then we want to go update the classifier head. So model dot classifier equals nn.sequential. So we're going to customize the classifier head with the values that we've got here. So first of all, foremost, it's going to be a dropout layer. P is going to equal dropout, and we're going to go in place equals true, because that's what both models have. Then we're going to finish it off with the nn linear. In features is going to be in features. And then we're going to also set the out features to be out features. So it's going to be the number of the class names. And then we're going to go set the model name. So model.name equals model name. And then we'll print out some info. F info creating model.name model feature extractor model, and then we want to return the model. All right, beautiful. Let's see how this goes. Let's create a model. Create model. Can we create an FNet B2 here? Equals create model. Model name equals FNet B2. And then we'll go FNet B2. Has no model efficient net B2. Oh, what did we get wrong here? Is this underscore? There we go. We've got an efficient net B2. Do we get a little printout there? Efficient net B2 feature extractor model. Yes, yes, yes. And then we want to go efficient net S. Wonderful. And then what if we just pass in fnet B4? Oh, I typed B2 by accident. B2. There we go. Okay. Beautiful. Let's just see if B2 has the right number of feature extractors down here. So, yep, there we go. And then if we change it to V2, V2S, we have, yep, dropout. Okay, beautiful. So now we have our models, or a function at least to create our models. So let's start setting up our list of experiments to run. So here in section 7.6, we'll just create that. And we might just comment out that. And then we might come up here and go here. Set up modeling experiments. Going to use similar code for our modeling experiments. Mainly want to substitute fnet B0 experiments with fnet V2S in its place. So we'll need a number of epochs. So num epochs. We'll keep these small again. Equals 510. And then models create models list. Models equals, here we go. This is nice and simple. Now we've set up the code in such a way that we can use very similar code to before, fnet v2s, and we have the same data loaders. So we'll just copy that in there. Wonderful. And then I think we only have one different step here. If we copy in this, so do you see what we're doing? We went through this code in section 7, PyTorch Experiment Tracking. So what we're doing is we're looping through the data loaders. So we're going through this for each data loader. And then we're going through the number of epochs, so 5 and 10 epochs. And then we're going through model name in models list here. But we need to fix this. So select the model. We'll go model equals create model, and then model name equals model name. So that's what we're changing from before. Instead of using an individual function to create each model like we did in the notebook here, we are using a single function to create a new model from scratch. Create a new model, or instantiate a new model, better yet. Instantiate a new model instance. And then the rest of our code should work fine. We're creating a new loss function each time we run an experiment because this is within all of the loops. So this is just going to run until all of the options in these 3 loops have been exhausted. And now you could write better experiment tracking code, but we're just keeping it simple to begin with. All we're doing is running 8 experiments. So each one of these is a different combination. 2 to the power of 3. Is that correct? I think that's 8. 2 times 3. Oh. 2 to the power of 3 is 8. Yeah, 8 different experiments. So then we train the specific model and we track the model we track the model's results using our create writer function, and we save the best performing model. Well, we save each model, and then we can inspect the best performing model later on. So are you ready? Let's try out, see how EfficientNet v2s performs against EfficientNet b2. 3, 2, 1, no errors. Let's run this. Oh, what did we get wrong here? Did we not put our model on the device? Equals create model to device. Did we put the model on the device? Maybe we just put it up to device here. Where's the best place to put our model to the device? I think we can go here, to device. Here we go, EfficientNet B2 feature extractor model. Oh, it's performing quite poorly here. Okay, what have we got wrong? This is good. None of our models are performing anywhere near to how well they did before. I think we might have something wrong here. So in here, I put the model to the device up there. Maybe that's a better place to do it. It shouldn't matter. Let's get a summary of okay. Normalize. I think this might be an issue here. Default. That should work. I wonder if we change this to manually set it to ImageNet. Or if we set this to toDevice. And if we set this down here to device. And let's get our summary parameters here. I always forget what these are, so I have to copy and paste them. Col names, row settings. So only the output layer here is trainable. That makes sense. Let's try this out again. Because this should perform quite well to begin with. Oh. Model equals. What do we got here? I am a little stumped at the moment, but that's all right. We'll figure it out. I might can that. No, that should be all right. Ah, forgot toDevice here as well. Our model's not learning anything. The loss is actually going up. What have we got different here? I think it's where we've created our data loaders potentially. But it shouldn't be. Data. Yeah, we've got images here. We freeze the layers. We update the classifier head. And we set the model name. We create the model name here. We return the model. I think there might be a bug in the latest version that we've got. Because the loss is going up here. Let's try the different model weights, hey? ImageNet 1K v1. This is going to take some good troubleshooting. I think the issue's in our create model function. I might restart the runtime and see what happens. Can any of you see what's going on if you're watching this live? That is bizarre. Unless our optimizer I think our data formatting might be incorrect. Let's go back to here. I am perplexed here. Creates a new model. Well, we've done the exercise. It's just that our model is basically guessing. Maybe we have to set the seeds? That shouldn't matter though. I wonder if I opened this in Colab and ran it end to end, what would happen? Because this, I literally was running the same code this morning. And it was working. So I'm just going to run this and see what happens. So we're getting a slight improvement here. Let's see what it looks like in TensorBoard, hey? Maybe the printouts are incorrect. We only want to view the test loss and the test accuracy. Look at that. That's all over the place. Okay, so our models are basically randomly guessing. So that is very, very strange. Is our optimizer optimizing our model correctly? Yes. Model equals create model. Let's see if this works. The original notebook that I literally ran this morning. What happens if I just create a model? Test model equals create model. I know that efficient net fnet b2. And if we go train, what we're doing here was we're troubleshooting why our models aren't training. Create a new optimizer right here. Torch optim atom test model dot parameters lr equals 0, 0, 1. Loss function equals torch dot nn slash or dot cross entropy. And then device equals device. We'll do it for 5 epochs. I forgot the name of the cross entropy loss. Do we have to restart the runtime here? Yes, we do. Writer equals none. It will be interesting to see if this model trains. My goodness. We've got something wrong here then. Okay, so there's something wrong in our model creation code, that's for sure. We can change this back to, I want to see, okay, let's get rid of let's just go, let's rip all of this out. Default. This is going to tell us whether our data or our model is incorrect. Now let's go freeze. And we can send this model to the device. Same thing here. Set the seeds. I wonder if that will change anything. Surely not. Oh. Hey, why did that just download some more weights? Okay. We've got a good performing model. Now, what have we done wrong here? Default. Default. Drop out. If model name equals EfficientNet B2, we set the model there. So this should be the exact same as doing this. Look, we've got weights equals that. We've got model equals that. We've got dropout. Yet if we do it outside of a function, it works. That has got me stumped. Well, there we go. Troubleshooting. This function doesn't work for us. So I'm just going to change this back to create fnet b0, b2. And then going to copy this. And this will be create fnet v2s. So let's can that. Let's can that. Let's go shift here. And let's can, no, that. This is for the top one. We want to just get rid of all that. So create fnet b2. We get that. Model name equals fnet b2. And then this one, I have no clue why that didn't work. Let's go fnet v2s. And that should be all we have to change. So now I should be able to go create fnet b2 with test model equals create fnet b2 which is the exact same as writing the code above, and it doesn't work. What? We've got the exact same code here. What if we kept going here? Test model equals create fnet b2. What if we set the seeds here? Is our return not in the right place here? So have a look at this. Let's just copy this exact code in here. Why this is not working. Create fnet b2. So that works. There is something here that we've missed. I think it could it literally be the tabs. I'm going to set this up as create model now. I think this might be a tab issue. I'm hoping it's a tab issue. Otherwise, I have no idea what just went wrong. So I want to run that, get rid of that, run that. What? So this code works. I need to see the difference between this. I've literally made a mistake here, and I have no idea what has happened. Compare diff. That's the original. And here's the one I just created. So let's go through this line by line. How do I edit? I'm going to cancel that, cancel that. Weight equals weight. Did I get that wrong by just typing in weight? That made no error. I knew it was something so simple. It's not this one. Weights equals weights. Oh, I'm a dummy. That whole time. Look at that. One parameter wrong. Oh my God. Okay. The function would have worked earlier, except we had a typo. So, classic. Let's just can everything. Make sure you write weights here and not just weight. So I'm glad we spent half an hour trying to troubleshoot that. Oh man, if we weren't using Colab, we might have an error for that. So now this should work. Oh no, this is still using the old function. Stop. So if model name equals fnet b2, model equals create fnet b2, else create fnet v2s. There we go. Okay, now we're getting somewhere. So the moral of this story is, instead of using Colab, maybe use VS Code. But the benefit of Colab is that we get a free GPU. So I can't believe that. How long do we spend on that error? Like 40 minutes? But that's why I do these live, so that you can see how I troubleshoot errors. And sometimes the errors are so simple. So simple. Now we need to step things up a notch and really finish this off. Experiment number 4. Who's going to win? EfficientNet V2S or EfficientNet B2? We can start to have a look at the next exercise too. Introduce data augmentation to the list of experiments. Oh, okay. So maybe we change up our list of experiments now from, instead of, we're going to not use the 10% data set. We're going to use a 20% data set, one with augmentation and one without augmentation. So that's what we'll do as the next experiment. We'll take the winner model from this and sub out our next experiment with data augmentation and not data augmentation. Experiment number 6. Who's performing better so far? EfficientNet V2S or EfficientNet B2? Oh, looks like EfficientNet B2's got the highest accuracy so far. We're watching models train. Oh, there's a good test accuracy value. So this is the penultimate experiment. FNet B2, data 20%, 10 epochs. We know that this was our best performing model last time. So here we go, the final experiment. The value to beat, the test loss to beat is 3960, and the test accuracy to beat is 9280. How's it going to go? EfficientNet V2S, double the amount of parameters as EfficientNet B2. Oh, we've officially got lower loss, officially. Oh, loss is back up. Still higher. Oh, it finished lower. With the highest, oh, with the clutch. EfficientNet V2S comes in with nearly 95% accuracy and the lowest loss value we've seen so far. We can view this all with TensorBoard, of course. Let's have a look. Is this a meme? The magic of the internet. What do we got here? Is this... That's what we could have had. We could have fixed that. Is that with... This is with PyCharm? We spent 30 minutes on that. Classic. That's what I'm going to do after finishing this course. I'm going to set up a great developer environment. Does PyCharm have Jupyter notebooks? Let's view all the test values here. We can filter this for test, actually. That's probably easier. Test. Have we got all the test runs? Yes, we do. Okay, let's get that out there. Oh, look at these models. What has the lowest loss here? Okay, let's inspect them one by one. Loss. We have test loss. Hey, all the values here? There we go. EfficientNet. You can see the highest one there is that green dot. EfficientNet V2S with 10 epochs has 95% accuracy. But the thing to note is that that model took the longest to train. So just keep that in mind. Not too much longer than EfficientNet B2, but we get a thereabouts 2 to 3% boostage points in accuracy for 1 more second of training. See you, Shavans. Thanks for tuning in. And then we go here. I don't think this is showing what we need. And I don't want smoothing. I just want absolute values. There we go. What gets the lowest there? Efficient net, V2S. There we go. Lowest loss. All right. So let's go. We're taking efficient net V2S, which makes sense that it gets the best performing. FNet V2S gets the best performance, lowest loss, and highest test accuracy. With 10 epochs and 20% of the data. See results. Beautiful. Okay, so now we're going to introduce data augmentation to the list of experiments using the 20%. So we're going to need to create two different data loaders. So to do this, we're going to have to alter the create data loaders function. So what we want here, let's write this down. What we want now is we want 2x different training data loaders, one with, we want one 20% data loader with augmentation, and then two, a 20% data loader without augmentation. And then we want to use FNet V2S model, and then train for 5 and 10 epochs. What would I recommend between TensorFlow and PyTorch? TensorFlow for basically almost everything production-wise. PyTorch is catching up though. PyTorch for research, but production follows research. So it's hard to recommend. I feel like TensorFlow has a bigger ecosystem, but PyTorch is definitely the king of research at the moment, and that is, it's June 2022. But that being said, they're very much quite similar. So if you're going for, like, you'd want to develop models that go into applications, I'd probably go TensorFlow or TensorFlow Lite. I believe that ecosystem is a lot more fleshed out than PyTorch. But if you want to research new architectures and build them quickly, PyTorch is probably your friend, because a lot of the research comes out in PyTorch. So let's update our data loaders scheme here to use different transforms per. Okay, so let's create our data augmentation transform. Data augmentation transform. So we want to let's use trivial augment with data augmentation. So let's use trivial augment, or should we use rand augment? Nah, PyTorch use trivial augment in their image classification pipeline. Let's use trivial augment. So torch trivial augment. We'll go in there. Data org transform equals, we'll go from TorchVision import transforms, and then we'll go TorchVision, we'll go transforms dot compose. And do we still have normalize? We're going to need normalize regardless, so we'll just get that down here anyway. Normalize, we want this. Normalize So normalize, we don't need that just yet actually. So transforms, we'll start with a resize, 224, 224, and then we'll bring in a transforms dot trivial augment wide, and then we'll bring in transforms dot to tensor. We'll see if this works, hey? And then we'll bring in normalize. And then let's go create a non-data org transform, non-data org transform, no data org transform. So the experiment we're checking here is whether data augmentation helps our model. So the previous experiment we did was we introduced another bigger model to see how if that improves, and we found out that it did. Now we want to know, okay, we're going to continue using that better performing model, EfficientNet v2s, and see if data augmentation changes our model's results in any way, shape, or form. So we'll start off with transforms. We'll do a resize, 224, 224, transforms, and then we can just go to tensor, and then we can go normalize. Beautiful. What did we get wrong here? Oh, this needs to be a list. Okay, so we can create the data loaders. Let's do this by updating data setup dot create data loaders. So let's import. We've got a function here in going modular data setup, which has been creating our data loaders. But let's change this to allow different transforms for different data sets. So we don't actually want to transform the test data set. We only want to transform the train data set. So train transform, we're going to put that parameter in there, and then test transform. So this is new, and this is going to be a transforms.compose as well, and this is new. So for the train data loader, the transform here is going to be the train transform, new. And do we get a doc string here? Transform. Oh, no. We put the transform in the create the data set. So now PyTorch is giving me, Colab is giving me variable errors. So test transform. So you see how now we've got a way to create just a train transform on the training data. New, only want to do data augmentation generally on the training data set. Beautiful. And then we go new, and we're going to go new. Beautiful. So that should work. So what we want now, we've got data org transform, and we've got no data org transform. So let's create our training, create train and test directories. Train 20% dir equals image path, which is a variable that we've got already, slash train, and train 20%, test. We'll use the 20% test directory now, equals image path test. Or should we? Do we have to? Yeah, why not? We're only using one test data set here this time. Yeah, that's okay. And then we want to create separate data loaders. So train data loader 20% with org equals create data loaders, and we want train dir equals train 20% dir for directory. Test dir equals test 20% directory, which is just those two variables we created here. The train transform here will be important, will be this transform we created up here, data org transform, and then the no data org transform will be for the test data set, and we'll keep that the same. Oh, we need to actually put test data loader 20%, and then the class names. Need to get all of those. Push that across. Then we'll push that right across. Test transform equals no data org transform, and the batch size, well, lo and behold, let's do our favorite batch size of 32 equals batch size. Okay, beautiful. Create train data loader with data augmentation. And now let's see what it looks like when we go create train data loader without. There we go. Beautiful. So how about we try visualize? Visualize different samples from both data loaders, org and no org. So let's see what this looks like. If we go, I believe we can go section 4 maybe. Let's go right down to the, we had a snippet of code in here. This, yeah, PyTorch custom dataset section 6. We wrote some code here to visualize transformed images. Yeah, that wasn't the function I wanted. Maybe it's in, oh, I know where it could be. In the old version of this notebook. Yeah, that was the function, view data loader images. So this is somewhere in here, view data loader images. Maybe it was in the helper functions. Let's go into here, PyTorch helper functions.py. Well, this is a way that we can visualize different samples, org and no org. And we'll change this to data loader. Might put that back into here. And then let's go view, check out samples with data augmentation. So what we're doing here is we're visualizing before we run experiments. So view data loader images. So I'm going to put in here this one, the with data org. Then we can do one without. So a little bit of augmentation here, not too dramatic. And then no data augmentation here. So that's, see, we've got a wrongly labeled image. That's not pizza. Hey, that's all right. That's what visualize. Check out samples without data augmentation. Now let's run some experiments. Run data org versus no data org experiments. So this time we want, maybe we do 10 epochs and 15 epochs. And then we'll get a similar setup to what we had before, but we're only going to use one model. And then this is data 20%. We want with org. Without org. And this will be train data loader 20% with org. And then without org. And then the model will be create model name equals fnet v2 v2s. So this will allow us to use the exact same experiment code that we did before. Excuse me. In models. Oh, that's what we want. In models. We'll run that. Now, so the next experiment we're running here is, we want to make sure that they're using the same test data loader. So let's make sure the test data loader is test data loader 20%, though it wouldn't matter too much if they weren't using it, because the test data loader is going to stay the same. New. Use test data loader 20%. So let's see how this goes. So model is EfficientNet V2S. Oh, what's happened here? Stop. Oh, num epochs. We're training for a little bit longer this time. Or maybe we don't. 5 and 10 seems all right. 5 and 10, that's fine. We should have kept going there. So we're starting with augmentation. Let's see what happens. Now, this is the beauty of machine learning. You can leave something running and go and come back. I'm going to go to the bathroom. I'll be back in a second. Oh, looks like this went a bit faster because we didn't have as many. What do we got? 1 minute, 17 seconds. Which model performed the best? Now, mind you, all of these test results are on a new test data set. Oh. Who has the lowest loss here? So it looks like without augmentation, so with aug, has a loss of 4716, but an accuracy of only 83.5. And well, let's view these in TensorBoard, hey? So load extension TensorBoard, and then TensorBoard logdir runs. Yeah, that's all I need. Oh. I forgot the flags there. So we're going to inspect our modeling results with TensorBoard. Taking a while to come up, that's all right. Now we want to filter our rungs for org, and we only want the ones with test. So which one finished on the highest? Okay, so it looks like with org for 5 epochs had the highest test accuracy. And which had the highest or lowest loss? With org, 10 epochs had the lowest loss. But without org wasn't far off. The loss value there for 10 epochs. And which finished the highest in terms of accuracy on the test? Okay, so without org for 10 epochs on EfficientNet v2 performed the best. Okay, I think that's what we run with for this final experiment. So now we've got a model that's working pretty well. So let me write down here. We've got a model that's working. Looks like, I'll just write up here. Looks like FNet v2s without data augmentation performed the best on average for test loss and test accuracy. Let's keep going with that model for the next experiment. So now we're going to scale things up. So we've slowly been building up different things or testing out different things for our FoodVision mini problem. But now we want to scale it up to FoodVision Big. So let's download the entire Food 101 dataset, which is 100,000 images, the biggest dataset we would have worked with so far, and take our best performing model, EfficientNet v2s without data augmentation, and we're going to try and train it for 5 epochs on Food 101. So the first thing we need to do is get Food 101 dataset. So let's go to PyTorch Food 101. This is where I've created the pizza steak sushi datasets from. I cut some data out of this, but now we just want to get everything. So we can set it up. Let's go. This might take a while to download. Train data equals Torch Vision. So we want to import Torch Vision. Datasets. Food 101. We'll download it to root equals data. And the split will equal train for the train data. Transform, we won't transform it yet because we can transform it when we load it in. And download equals true. And then we'll get the test data as well. Or maybe we should put a transform here. Yeah, we'll create a simple transform. Oh, we'll get our simple transform down here. Look at all these modeling experiments we've done. Download and transform Food 101 data. So this is where we can put a transform in here. Transform equals simple transform to make sure all of our data is in the same format as ImageNet. Oh, lucky we got a typo there. So we're not using data augmentation here. We've got a model that's working, FNet V2S, pretty well. So now let's turn our FoodVision mini model into FoodVision Big by upscaling the data. Specifically, let's train a FNet V2S feature extractor on all of the Food 101 data. And we'll do so, we'll do so for 5 epochs without data augmentation. We're going to download that. That is going to take about 3 minutes or so, but while that's loading, we can start to create the data loaders. Create data loaders. Now, I might increase the batch size here. Let's try a batch size of 128, just so we can use as much of our GPU as possible. What GPU do we have actually? NVIDIA SMI. And we'll go train data loader big equals torch.utils.data loader, and we'll go train data, batch size equals batch size, and then num workers equals, I'll get OS in here as well, import os.cpu count for how many CPUs we have. I think that should be enough for that. Where's our create data loaders function? What did we put in there? Def create data loaders. Yeah, well, we want to shuffle. Yeah, let's shuffle the training data and pin the memory. That's a good idea. Pin memory is going to be pretty good here because avoid copies of the data in and out of memory where possible for speed ups. So one of the biggest areas where you get code slowdowns is where you copy data in and out of memory. So that's what pin memory does, is anytime we don't have to copy data in and out of memory, it's going to not do that. So it's going to pin memory in the GPU where we can. Because if we want to train a model this big, we want to use as much of our GPU as possible. I'm not going to shuffle the test data here actually. Batch size equals batch size. Num workers equals os.cpu count. Pin memory equals true. Wonderful. We'll run that and then we'll create the model. So we can actually create this model FoodVision Big. It's just going to be an efficient net equals create fnet b2. But we need to update the head, don't we? TorchVision.models fnet v2s weight equals torchvision.models.efficientnet efficientnet v2s dot or weights dot default dot, we want this one to be efficientnet v2s weights equals weights GHTS to device FoodVision Big Model. Let's call it Big Model, hey? FNet V2S weights. I'm not sure how long this will take to train. We'll freeze the base layers. For param in dot parameters or features. Features dot parameters. Param dot requires grad equals false. Change the classifier head to suit 101 different classes. So we're going to set the FoodVision Big Model dot classifier is equal to nn dot sequential. In here we're going to have dropout p equals 02, and then linear in features equals 1280, out features equals 101 output classes for food 101. So we've created our data loaders. We've got a pretty big GPU here, so that should be good. Note this may take 5 minutes in Google Colab. So we've got our data downloaded. We've got our our data loaders created for FoodVision Big. We are now updating the classifier model here, and let's make sure this is on the device. To the device, and let's inspect FoodVision Big Model. Let's see what happens. What do we get wrong here? EfficientNet V2 S. That's what we want. Three Fs. There we go. Look at our big model. Woo! So let's get a summary of our big model, hey? Summary model equals FoodVision Big Model, and input size equals 13224. See what happens. There we go. We have our biggest model yet, 129,000 trainable parameters with 100,000 images. Maybe the batch size could be higher here, 256. Let's see what happens here. Let's see if this will train. So now we can go how did we create a writer before? Create writer. FoodVision Big results equals train, and we want model equals FoodVision Big Model, and then train data loader equals train data loader big, test data loader equals test data loader big, optimizer equals torch.optim.atom. We'll go FoodVision Big Model dot parameters, and the LR can be 001, just like we've done before. Loss function equals torch.nn cross entropy loss, and then device equals device. Epochs equals 5, only 5 epochs for this big model to start off with, and then the writer can equal create writer. Experiment name equals, we'll call it FoodVision Food 101, all data. And then model name can be FoodVision Big, and then epochs. Oh, all right. Let's see where this takes us. The biggest model we've built yet. FoodVision Big. 3, 2, 1, go. Is this going to fit? Oh, what did we get? Oh, excuse me. Params. Here we go. Food 101, all data. I'm going to open up a terminal here to track NVIDIA SMI. Watch. N1. NVIDIA SMI. So we're not using as much as the GPU as I would like. It keeps going in and out of 100. I think we could even increase the batch size here to be 1,000. So we've got GPU usage here. I think every time it goes through a test batch, it goes to 0, maybe. But that doesn't make sense because it's supposed to use the device. I think I might up the batch size here. We've done 256. I think we could handle, a GPU can handle 512. Because see how much room we've got in the memory here? Is it worth stopping? Stop. Let's step this up to 512. Now we're using a batch size of 512. See if this changes. Oh, not really. Oh, there we go. So altering the batch size to 512 means we'll get through the data a lot quicker. So if we check, Food 101 has 100,000 images. We'd be very close to doubling the batch size again. So we'd have 1,024 batch size. So let's leave this run for a little bit. We can chill out and just let this run and talk. That's the beauty of machine learning, is that you could go and chill if you wanted to. Now that we got it training, go for a walk, come back. But look at that. We have, once this finished training, we've completed the exercises for 07 PyTorch Experiment Tracking. So we started up here, pick a larger model to train with. So we prepared all of the data here. I might just write this down. get various imports and helper functions. Just going to put some headings in here while our model is training. Have we made it through an epoch yet? We haven't made it through an epoch yet. Okay, I'm gonna let this go. I'm gonna let it go for one epoch, and then we can finish this video. See how it goes after the first epoch. I'm going to put this visualization code in the helper function section. So for me, this is saying that if we're getting spikes in the GPU usage, I think our data loader code could be improved. That would be something to think about. So we've been going for just under 8 minutes now for this, a single epoch. So this model might end up training for about an hour or so. But I'm not going to sit here and watch all of that. I'm going to let it go for one epoch, and then I'm going to go for a bike ride. Hello, Nifisme. We can talk in the chat. How many people are here? 5 viewers. Anyone watching this live have any questions? I'll put the chat over here for Twitch for the next 5 minutes or so while we wait for this epoch to go through, just to make sure it worked. I mean, we could end it here because our model is training on FoodVision Big. But let's keep going for fun. What would be the perfect tech stack for a machine learning MVP? Well, it depends what you want to build. If you just want to show your modeling, like a demo of your model, I'd recommend Gradio. This is my favorite, Gradio. You can get started easy. Hosting, it's used almost everywhere. Heap of good reviews. Let's try it out. Play with DALL-E Mini. And type in my name, Daniel Burke. AI model generating images from any prompt. Let's have a race between epochs and DALL-E Mini. Crayon.com. Why is there ads on this site? There we go. Okay. Apparently that's what I look like. According to DALL-E Mini. We haven't got an epoch yet. I didn't expect it to take this long to train. How long should we wait for an epoch? This is a big model. This is 100,000 images. A feature extractor model. Now, let's go. PyTorch machine learning course logo. What logo could we have? Oh, there we go. So beautiful. Have a look at that. We finished one epoch of FoodVision Big. So I'm going to let this train, and you'll be able to find this notebook in GitHub, on the course GitHub. So find the notebook on the course GitHub. Of course, this will be finished by the time you find this notebook. So this will be under extras, under solutions, and it'll be under here, number 7. So this is PyTorch tracking exercise solutions. So I'm going to put this link here. But that is the walkthrough. Why didn't that turn into Markdown? There we go. That is the walkthrough of the exercise solutions for PyTorch Experiment Tracking. Albeit it did take us, how long? How long have we been streaming for? Just under 3 hours, but we spent about half an hour going through a typo, basically. So just be careful when you're putting in your parameter names. If you're using Google Colab, the error or the debugging messages aren't that great. So if you run into errors and you don't know why, I need to remind myself this constantly to check the parameter names or the variable names. So I'm going to let this run for a little bit more, and I'm going to put the solutions up on GitHub once it's finished. But, oh, there's some pretty cool logos. So that's Daily Mini. Check that out. And to finish off, if you want to deploy your machine learning models, I'd recommend checking out gradio.app. But thank you so much for tuning in live. If you're watching this at a later date, let me know if you have any issues on the GitHub discussions page on PyTorch Deep Learning. You can post a discussion there. And I'll see you next time. Peace.